Our final approach to writing electron configurations uses a method known as orbital box diagrams. So we're just going to jump right into looking at an example of drawing an orbital box diagram. When you were first learning about orbitals and sublevels and letter designations, I had suggested that drawing boxes can be a helpful way for visualizing orbitals, and that's really what drawing orbital box diagrams is all about. So for example, we're going to look at drawing an orbital box diagram here for carbon. And here's a periodic table to help guide us along our way. We'll notice here when we find carbon on the periodic table that it's in the 2p block. It's two elements or two groups into the 2p block. So it will end with 2p2. So if we think about what its electron configuration would be, it would just be 1s2, 2s2, 2p2. But as far as drawing the orbital box diagram, we really just think about it the same way, except we try to visually depict each electron. So we do that by drawing a box to represent an orbital. So the first sublevel to fill is the 1s sublevel. So I label it 1s and I draw a single box to represent the one orbital that makes up the 1s sublevel. And because the electron configuration is 1s2, we know there are two electrons in that 1s orbital. So to represent electrons, we're going to draw arrows. We'll have an up arrow and we'll have a down arrow. And there is a significance to that. As it turns out, electrons have a magnetic spin to them. And that spin can either be one of two directions, which we refer to as positive spin or negative spin. So the up arrow designates the positive spin. The down arrow designates the negative spin. Magnetic field direction. If you have two electrons in an orbital, they must be opposite spins. In other words, we could not put two positive spins or two up arrows in the same orbital, nor could we put two down arrows or two negative spins in the same orbital. They must be opposite. So this represents our 1s2. Then we would have 2s2. Now again, it's an s sublevel. So we are going to have just a single orbital, a single box, and we'll have two electrons there, a positive spin and a negative spin. Now comes the 2p. Now recall, p sublevels have three orbitals, so we draw three boxes, as you can see here. Now we know the configuration is 1s2, 2s2, 2p2, so we're only going to have two electrons in this 2p sublevel. The question becomes, which orbitals do we put them in? And what spins do they have? They're going to have positive or negative spin. Well, by convention, meaning just the way we always do things, we always start with the first orbital. So we put an electron in that first orbital. Now we have a decision to make. The question becomes, where does that second electron go? And ultimately there are three options. Option number one would be we pair it up in the same orbital. And if we were to do that, we would have to have a negative spin because we already have a positive spin in that orbital. A second option would be we put it in a different orbital with the same spin. So in other words, I could put it in this second orbital here with a positive spin, or I could put it in the second orbital with a negative spin or a down spin. And really the reasoning would be the same for this third orbital. It would be the exact same as putting the second. So there's three options. Same orbital, which would have to be opposite spin. Different orbital with either the same spin or opposite spin. And as it turns out, it does matter what the answer to that question is. The answer is governed by what we call Hund's rule. Hund's rule says the following, that we have to put single electrons with the same spin, and they must occupy each degenerate orbital before pairing opposite spin electrons in the same orbital. This word here, degenerate, simply means the same amount of energy or equal energy. I will have you recall when we were learning about sublevels and orbitals that we said that the orbitals within the same sublevel, so we're talking about these three orbitals here in the 2p sublevel, they all have the exact same amount of energy. In other words, they are degenerate. So following Hund's rule, we need to put a single electron.
Erica Jordan.
We need to put a single electron in each orbital, all with the same spin, before we go pair up the electrons. So the answer here for carbon is that that second electron in the 2p must go in a different orbital, and it has to have the same spin as the first one. So if we had started with a negative spin, which there's no rule that says we couldn't, if we had started with a negative spin here, we also would have needed a negative spin here in the second orbital. All right, let's do another example. We'll draw an orbital box diagram for vanadium. So once again, we want to find vanadium on the periodic table. Here we can see it. It's in the 3D block. It's 3 elements in, or 3 groups in, so it's going to end with 3D3. Everything before that will be filled up. So we just do it just like an electron configuration. Start with 1s. There's 1 orbital there, so 1 box. 2 electrons, positive, negative spin, 1s2. Now we have 2s2. Again, positive spin, negative spin. Now we have 2p. Now at this point, it's going to be filled. It's going to be 2p6. But I would encourage you, when you go draw the electrons in, draw them in a way that matches Hund's rule. In other words, I'm going to put a single electron, all with the same spin, in each orbital first. Now I'll go back and pair them up. It just gets you in the right habit of applying Hund's rule correctly. Next we'd have 3s, and there'd be 2 electrons. Then 3p. Same thing as before, 1 electron in each orbital, all with the same spin. Then pair them up. Now we have 4s, and again, just 1 orbital there because it's an s sublevel, 4s2. Now we get to the 3d. This is the first time we've seen a d sublevel. Recall d sublevels have 5 orbitals, so we need 5 boxes. And we need 3 electrons because we said it was going to end with 3d3. So applying Hund's rule, those 3 electrons will go in 3 different orbitals, all with the same spin. So this should be our orbital box diagram for vanadium. Let's take a look at one more example here. Here we're asked to draw an orbital box diagram for platinum using noble gas notation. So you've just learned about noble gas notation. You can apply that same idea to orbital box diagrams. So when I find platinum here on the periodic table, which is atomic number 78, I'm going to start by putting the symbol for the previous noble gas xenon in brackets. And just like the other noble gas notation, this just represents all of the electrons in xenon's configuration. From there, we will pick up with the 6s sublevel, because that's the first one after xenon's electron configuration. So that would be 6s2, because there would be 2 electrons there. Now we get to the 4f. And like before, the first time we've seen this particular sublevel, consider the number of boxes. There are 7 orbitals, 1, 2, 3, 4, 5, 6, 7. So we need 7 boxes there. That's going to be 4f14. It's going to be completely full. So again, when you draw the arrows in, apply Hund's rule, fill each orbital with a positive spin first, or it could be all negative spin, it really doesn't matter, and then go back and fill with the opposite spin. So there's our 4f14. And then when we find platinum here on the periodic table, we'll see that it should end with 5d8. So our 5d sublevel, the 5 orbitals, we're going to put 5 electrons in, all with the same spin in separate orbitals. Now we'll go pair up our 6th, 7th, and 8th electrons will be paired up at negative spin. So you should end up with 2 unpaired electrons in the 5d sublevel there. Alright, just want you to get some practice now. For each of these, pause the video once you see the element, draw the orbital box diagram, and then go ahead and play it and see if you got it right. Alright, first one is sulfur. Your orbital box diagram should look like the following. Sulfur's configuration will end with 3p4. We can see it here, 4 elements into the p block. So it will be 1s2, and you can see the 2 electrons there, 2s2, 2p6, 3s2, 3p4. Notice there we have 1 electron in each orbital with a positive spin, and then just a single electron is paired up with a negative spin. In other words, I don't put 2 electrons in 2 orbitals and leave the third one empty. Alright, next one is iridium, and go ahead and use noble gas notation here. Alright, the previous noble gas from iridium is xenon. Iridium we can see is here on the periodic table, atomic number 77. So it should end with 5d7. That's what it should end with. End with if my counting is right there. And the previous noble gas is xenon. So xenon ends with 5p6. So we'll start with 6s. So 6s2. Then your 4f sublevel would be completely filled, 4f14, and then 5d7 because it's 1, 2, 3, 4, 5, 6, 7 elements or 7 groups into that 5d block there. And so you have 5d7.